Hello, and welcome to my talk called Communication Efficient Triangle Counting Under Local Differential Privacy. This is joint work with Takao Murakami and Kamalika Chaudhuri. This work is about counting subgraphs in a network. We focus on triangles and K-stars. A K-star consists of a central node connected to K other nodes. In this example graph, the light green user in the middle, is a part of three 3-stars. And there are 2 triangles, 15 2-stars, and 6 3-stars. Even with these simple coefficients, we can already compute interesting quantities about the graph, such as the clustering coefficient. This is the probability that 2 friends of a user are also friends, and it's useful for friend suggestion. It's given by 3 times the number of triangles divided by the number of 2-stars. We can imagine that revealing the number of triangles or K-stars can reveal sensitive information about the graph. To mitigate these privacy issues, we can use local differential privacy, in which a user obfuscates her own data with no trusted third party. This is illustrated in the bottom left. Unlike central differential privacy, illustrated in the bottom right, we don't need to trust a central aggregator, and the aggregator can even be adversarial. Prior work shows that K-stars can be estimated accurately under LDP, and triangles can be estimated accurately under LDP, in which users are queried twice. However, for triangles, the download cost of this algorithm is large. It takes 400 gigabits on a realistic graph, which would take 6 hours to download. Thus, our contribution is that we dramatically reduce the download cost using several new algorithmic ideas, and we reduce it down to 160 megabits, which takes just 8 seconds. I will start with some preliminaries. In our setup, we represent the graph as an adjacency matrix where 1 indicates an edge. The graph is distributed locally, so user VI only knows her neighbor list AI, the ith row of A. We have illustrated this on the simple example with 4 users. To compute an answer, an aggregator who does not need to be trusted asks users questions in the form of a randomizer Ri. User I applies Ri to her data AI and sends it to the server for aggregation. The way that privacy is protected in this model of computation is that each randomizer satisfies epsilon edge LDP. Epsilon edge LDP states that if an adjacency list differs in 1 bit, then R of A and R of A prime are similar distributions up to epsilon. Technically speaking, each edge is part of 2 adjacency lists, and therefore changing 1 edge affects 2 adjacency lists in the graph. However, our algorithm uses just the lower triangular part of the adjacency matrix, so epsilon edge LDP protects the distinguishability of an edge up to epsilon. Now I will overview the existing triangle counting algorithms under LDP. Notice that triangle counting is not easy in the LDP model because no user is aware of any triangle. They cannot see the third edge between their neighbors. To overcome this, in the first round, the user applies randomized response to each bit of their neighbor list and releases it to the server. This produces a noisy graph, a graph consisting of noisy edges. And as a reminder, randomized response, you simply flip whether an edge exists or not with some probability. In the second round, each user counts triangles using 2 of their edges, and the third edge, the one they don't know, coming from the noisy graph from the first round. The user sends the number of noisy triangles plus a corrective term for debiasing plus Laplace noise to satisfy LDP to the central server, and the server simply sums these up to obtain an unbiased estimate. However, in order for users to perform this round, note that they must download the edges from the first round in the noisy graph. This noisy graph is dense, and it is extremely large, and it is prohibitively costly. Now I will outline our proposed mechanism. In our approach, we will form a sparse noisy graph G prime in the first round. This will reduce download, but will increase estimation error. To form the sparse noisy graph, we perform what is called asymmetric randomized response, which is effectively sampling edges after randomized response is done. So we take edges that are reported to exist by randomized response, and with probability 1 minus P2, we change those edges to a 0. This is illustrated in the bottom left part of the graph. And this is post-processing of randomized response. Therefore, it still satisfies DP. After this, our second round uses 2 further improvements to reduce error. They are called selective DL and double clipping. In selective download, consider what happens when a user downloads the entire noisy graph and counts triangles. If we have the following 4-cycle shape illustrated in the bottom left, then the noisy edge between Vj and Vk will cause 2 triangles to appear. Thus, the error is tied to the number of 4 cycles, which is n times Dmax cubed, the maximum degree of the graph. If instead user Vi only downloads and considers edges Vk and Vj, where ijk is a triangle in the noisy graph, then it is much less likely that all 5 edges will activate and produce 2 false triangles. This makes the triangles a less correlated event with each other, allowing us to reduce the error to n times Dmax squared. This is what the algorithm ARR2NS does. And we also consider a variant ARR1NS, in which a user Vi downloads an edge Vk and Vj when just 2 of these edges are in the triangle in the noisy graph. This algorithm can perform better experimentally. In the second round of the algorithm, users add Laplace noise to their noisy triangle counts. When the graph is heavily downsampled, we expect the sensitivity of the number of noisy triangles to be less because degrees are often less than Dmax, and the graph is sparse due to downsampling. We achieve this sensitivity reduction using clipping techniques. We clip edges and then we clip noisy triangles to get away with adding less noise. For edge clipping, we estimate a user's degree before the algorithm even runs and tell the user to remove edges if his degree is higher than the estimate. This allows sensitivity to depend on the user's degree as opposed to a global constant. For noisy triangle clipping, if the number of noisy triangles of a user exceeds some constant kappa I, then we reduce the number of noisy triangles by clipping, so he will only send a maximum value of kappa I. We set kappa I so that the probability of actually clipping is very small. In the example, the user has clipped 2 of his edges and capped the number of noisy triangles to 3 and has also capped his degree to be 4. These clipping techniques add bias to our algorithm, but we sent them so that the clipping rarely occurs and it still allows for less sensitivity. Now I will outline our experiments. The datasets on which we ran our experiments were the Google Plus social network and the IMDb database, consisting of matchings between movies and actors. These graphs have hundreds of thousands of nodes, and like many real-world graphs, they are sparse. We have plotted the relative triangle count error versus the download cost of the various algorithms on the 2 plots below. We can see that with the double clipping technique, for just 19 megabits for Google Plus or 160 megabits for IMDb, the relative error is much less than 1. We contrast this with previous work, which required users to download hundreds of gigabits and appears as the square on the bottom right of each graph. Note that the error of this previous work is higher than our double clipping techniques because it does not utilize double clipping, and this indicates that double clipping is an effective way to reduce error. In our second set of experiments, we evaluated the effect of selective downloading. We fixed the download budget and ran the full download of the previous work versus ARR1NS and ARR2NS and collected their relative errors. The plots indicate that selectively choosing the download can significantly reduce the error by a factor of 2 to 4. Also, ARR1NS outperforms ARR2NS because its sensitivity is more effectively reduced by our double clipping technique. In conclusion, we proposed a communication-efficient triangle counting algorithm under LDP, which reduces download costs from 400 gigabits to 160 megabits, while still maintaining low relative error. And for future work, we would like to consider more effective triangle counting with one round of communication. Notice that our techniques use two. I'd like to thank you for your attention.